Hello friends, from this lecture onwards we will be considering or looking into a new module wherein we will try to explore the areas where data analysis or data science can be introduced or has been introduced in materials research. Now when you consider the overall role of data analysis in materials research, it can broadly be categorized into two. So the data science or data analysis in materials research, one is largely been employed. So one area where the data analysis is used to is to understand the fundamental behavior of materials. So it is used in fundamental researches wherein our goal is to understand the behavior of the material in under a given circumstance or under a given condition. And the other area where the data analysis is used is rather an application oriented aspect, wherein we are attempting to develop a material or an alloy with a given set of properties that exhibit a given set of behavior. In order to develop such alloy with the desired properties, we are using data analysis techniques or largely data driven studies. Now, as a way of getting into this data analysis, as a way of understanding where these data analysis are being employed and what is the underlying governing factor, let us try to rather consider or build us up to the data analysis by considering the building blocks of this entire data analysis and entire data driven processes. So most of or almost all of the data driven analysis, they are rather a different variant of using statistics to understand the data that is presented to us. So what essentially data analysis is rather the application of the statistics. So therefore, what essentially we will be doing in the initial introductory lectures of this particular module, wherein we are trying to understand the role of data science, we will be trying to gain the fundamental understanding, or we will be trying to look into the fundamental aspects of statistics that ultimately translates to the data analysis. So in this lecture, we will focus on the building blocks, so to speak, of the statistics, which will ultimately lead to or which will ultimately contribute to the data driven studies in materials research. Now without further ado, let us begin with rather a case study or a scenario, a plausible scenario that you might come across while during your materials research. So what essentially you are doing is you are trying to create a new alloy. Let us consider an alloy of say cerium and lanthanum. I don't know if they are completely soluble or miscible or not, but just for the sake of discussion, let us consider you are working on two new elements and you are trying to rather consider its miscibility. You want to build an alloy, you want to conjure up an alloy based on these cerium and lanthanum, based on these two elements. Now, while you are trying to build this alloy, while you are trying to develop this alloy, you wanted to know what would be the lattice parameter of the specific alloy when I have X amount of lanthanum present in cerium. So you are playing around with cerium and lanthanum, and you are trying fixing one as a base metal and playing around and changing the composition of the other alloying element. And now what you want to know is you want to know what could be the lattice parameter for this alloy that I am trying to build. Now fortunately for you, you have several such alloys, like you have previously built several such alloys with varying compositions. So you have built an alloy with cerium X1 lanthanum, cerium X2 lanthanum, cerium X3 lanthanum, and so on and so forth. You have cerium Xn lanthanum. So many alloys you were able to build earlier, and now this is the alloy that you have recently built. So this you have built earlier. So many alloys you have developed earlier. So you have developed n alloys with a different combination of cerium and lanthanum. Now, unfortunately, even though you have done all these research, even though you have developed n alloys, unfortunately, you fail to rather note which material pertains to which alloy. So you have created blocks of each of these alloys. But since unfortunately what you fail to do is you fail to label these blocks. So you have created n such blocks, each pertaining to one of these alloys. So you have created n such blocks, each pertaining to one of these alloys, but what you have done is you have failed to label what this alloy is, failed to label which block pertains to which alloy. So in this case, you want to predict, or you want to rather give an estimate of a random, a ballpark of an approximate estimate of what could be rather the value of the new alloy that you have developed. So the condition is you have developed n alloys, you have built blocks of n alloys, but you have failed to label it. So essentially what you have is n different blocks of alloys, and you have n different blocks of alloy, you essentially have n different lattice parameters. And from this lattice parameters, you want to see if it is possible for you to provide a random estimate, rather an estimate of what could be the lattice parameter of this new alloy. So in this condition, let us see if we are able to rather, using some statistics, if we are able to rather provide an estimate of what could be the lattice parameter of this new alloy which you have developed from the n alloys that you have developed and you have failed to label it. So such is the condition. So in order to do that, what we can essentially do is we can estimate the lattice parameter. So this lattice parameters of the all n alloys that we have previously developed is available to us. So let us rather look into the lattice parameters of all the n different alloys that is available to us. Kindly note that, and let me remind you, we don't know which lattice parameter pertains to which alloy specifically because we failed to label it rather. So essentially what we have is we have n data, and we don't have any corresponding data on the alloy composition that leads to this lattice parameter. So all that you have is a set of n lattice parameters in no order. So in that case, using this this data set, which is just comprises of the lattice parameter alone, there is no associated variable to it, just the lattice parameter, one single independent variable alone, and using this we want to estimate what could be the lattice parameter of the newly developed alloy. Let us see if it is possible for us to do that. Now in order to do that, what essentially we can begin with is we can consider rather a scale which includes all the lattice parameter that we have estimated so far. So what essentially we are doing is we have n lattice parameters. So in purely technical sense, we have n independent variables. We don't have any dependent variables, we just have n independent variables, and we consider the maximum and minimum of this independent variable, and we create a scale from that. We just look into those n independent variables, and we consider, let us say we arrange it in the increasing order, and based on that we create a scale that includes, or that rather has the minimum and maximum of this lattice parameter. So we have created a scale. Now what we can do is onto the scale, it is possible for us to place the lattice parameter according to their position. Supposing if you find a lattice parameter to be 2.03 angstrom, you have placed it here. So this lattice parameter, you have placed it here. And if you find, and you also find there is a lattice parameter, an alloy with a lattice parameter rather 0.38 angstrom, you have placed it here. So what essentially you have done is you have considered all the n data set, just one, if you write it down on an Excel sheet, it will be just a one column data set. And this one column data set, or this vector rather, if you wish, we consider the maximum and minimum of it. We build a scale, and onto that scale we are placing the corresponding n variables. So one variable is 0.23 angstrom, we have correspondingly placed it here, and the other variable is we have 0.38 angstrom, we have placed it here. So we have created a scale based on the range, and then we are placing the corresponding lattice parameters onto this scale. Now when you place all the n lattice parameters that was previously known to us, so we have n lattice parameters that we are previously aware of, these are known, and these we have placed it onto the scale that we have built, and this is how the population distribution, so all these data sets, all these data points, we refer to it as the population. So this is how the population is rather distributed. This population is rather distributed on the scale that we have created. So we have created a scale, we have been placing the lattice parameter onto the scale based on the magnitude, And this is how the distribution of the population is. The population here meaning the data points of the lattice parameters. So this is how the data points of the lattice parameters are distributed on the scale. Now based on this, you could say, at least we could qualitatively, we could guess that this region appears to be more densely populated than this region and this region. And this region, the one that has been rather shaded off, this region is rather more densely populated than these two regions. However, we cannot accurately say how much densely it is populated. It just appears to be densely populated because we are not able to, one data points overlap largely with other in this region. So we could say that this region is densely populated only qualitatively. We cannot say anything quantitatively, but qualitatively we can state that this region is rather densely populated than the other regions. So when you want to have a quantitative description of which region is densely populated and we want to quantitatively describe which is the most populated region, then it is possible for us to do so by creating something called as bins. So what essentially we can do is, on this scale itself, it is possible for us to create something called as bins. So what essentially the bin does is, the bins are nothing but the range of lattice parameters. So what we essentially have in the scale is rather a continuous change in the lattice parameters. So what we introduce now is, we introduce a range of lattice parameters and call it as a bin. So in this case, each bin has the width of 0.05 angstrom. So this first bin, it ranges from 0.05 angstrom to 0.1 angstrom. The second bin, it ranges from 0.1 angstrom to 0.15 angstrom. And the third bin, it ranges from 0.15 angstrom to 0.2 angstrom. So what essentially we have is, instead of considering all the lattice parameters, now we have created bins, and these bins have a specific width associated with it. So the bins, they are essentially a range of lattice parameters and they have a specific width associated with it, and that specific width is 0.05 angstrom, and the range, depending on the position of the bin in this overall scale, the range of the bin would vary. In the early stages, it is 0.05 to 0.1 angstrom. At the end, towards the end, what we have is 0.45 angstrom to 0.5 angstrom. So what we have done is, we have rather separated the entire scale into different bins, and that the bins have a specific width, and the range of these bins vary as you move along the scale. Now what can be done is, now the lattice parameter that populate a given bin can be stacked one over the other. So the lattice parameter that fall into a given bin can be stacked one over the other, and this will ultimately lead to what we refer to as the histogram. So this is what we refer to as the histogram, and this histogram now comprises of, it rather shows the population of the lattice parameter within a given bin in a more evident manner, in a more clear way. So what we can say is that, based on this representation of the population of the lattice parameter within a given bin, we can say this bin here, this bin that is between 0.25 angstrom to 0.3 angstrom is the most populated bin. And the second most populated bin is this one, which ranges from 0.3 to 0.35 angstrom. So what we have done is, by starting off with just placing the lattice parameters into the corresponding position on the scale, now we have transformed that representation to the histogram by introducing something called as a bin. By introducing bins which rather separate, or it rather groups the certain lattice parameters of a specific range. Now what we have done is, we have introduced this bin and we have considered the population within a given bin, and this population is now, instead of rather collectively represented, they are stacked one over the other, so that it is rather easy for us to perceive which bin has the most population, and this representation is called as the histogram representation. Now what essentially is the advantage of histogram representation, because we should not forget our initial question, that is, now we have a new alloy, that is cerium X lanthanum, and we want to at least say what could be the estimate. We just want to say what could probably be. So the term here is probably be the lattice parameter of this new alloy that we have developed. We don't want to give an exact value, but we want to say this could possibly be the value of this particular alloy. So that is what our goal was, and for that we have been doing all this, and now we have ended up by constructing an histogram. Now what this histogram helps us do is, this histogram helps us say that the alloy that we have developed, that is cerium X lanthanum, the probability of the lattice parameter of this alloy lying within this range is higher, because in this range most of the lattice parameters populate this category of bins. So in this combination of bin ranging from 0.2 angstrom to 0.4 angstrom, what we essentially have is the most population of this lattice parameter. So from that we can state possibly this alloy that we have newly developed, the lattice parameter, probably the lattice parameter of this will lie within this range here, because our experience, so whatever studies that we have done so far, the data that we have developed so far, it is rather densely populated within this range, and therefore from this population I can state, or we can rather claim, that the probability, again the term, what probably could be the dimension, the lattice parameter of this alloy now has turned to the probability. So the probability of the lattice parameter of this newly developed alloy falling into this range is greater than the other bins. This we are able to state because this particular combinations of bins that ranges from 0.2 angstrom to 0.4 angstrom, the population within this bin is rather much denser when compared to all the rest of the population. From that we can state that the probability of the lattice parameter of the newly developed alloy lying within this range is greater than all the rest. So essentially what this histogram representation helps us do is, this histogram representation, in addition to making it visible for us to claim where could possibly be, or what could probably be the new lattice parameter, it helps us make a definite probability calculations. So we now know that in this range, in this bin that ranges from 0.25 to 0.3 angstrom, the population, so most of the alloys, the lattice parameter of most of these alloys range in this, or in this, or most of these lattice parameter, they fall between this range here, and the second most is between 0.3 and 0.35 angstrom. So what it essentially this particular histogram representation help us understand is, it helps us visualize which is the most populated range of lattice parameter, which lattice parameter does most of the alloy assume for our given case. Now from that it is possible for us to quantitatively, so even though this gives us an illustration, from the histogram it is possible for us to quantitatively state what is the probability of the new alloy assuming a lattice parameter within this bins here. So we have separated the entire scale into different bins, and it is possible based on this histogram representation, based on the way we have devised this, the way we have presented this data, this representation help us quantitatively state what would be the probability of a given alloy assuming a lattice parameter of a specific range. Now supposing the range we are interested is in the most populated or the most dense range, that is 0.25 to 0.3. So this is the most dense range. So the probability of the lattice parameter, new lattice parameter, assuming a value between the most dense range, is the way we can estimate it is by considering the population in the most dense range, or in the most dense bin, dividing it by the overall population. So when you take the ratio of the population in the most dense bin and take the ratio of it with respect to the overall population, that will help us understand, or that would help us quantify what could be the probability of the lattice parameter of the newly developed alloy to fall into this category here, to assume at this range here, to assume this densely populated range here. So this understanding can be extended to any bins. Now when you extend this understanding to, say for instance, the bin that ranges from 0.4 to 0.45, if we have to estimate what is the probability of the lattice parameter of the newly developed alloy to assume a value between 0.4 to 0.45, what essentially we need to do is we need to calculate, we need to estimate the population within this bin. In this case it is rather small, 3, and we have to know how much the rest of the population is, how much is the total population. So we have to sum all this up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there are 10 different bins, and we have to consider the population of all these bins individually and sum it all up. So summation of all the 10 different bins, so 1 to 10, so I is each of the bin, the population is each of these bins, and we have summed it all up. So this will give us the probability of the lattice parameter of the newly developed alloy to lie between the range of 0.4 to 0.45 angstrom. So 0.4 to 0.45 angstrom. So what could be the probability of the newly developed alloy, assuming the lattice parameter within this range, can be estimated by this quantitatively by this expression. So what histogram gives us is, in addition to rather graphically representing the population of the lattice parameter in a range of bin, it also helps us quantitatively define or describe the probability of the newly developed lattice parameter or newly developed alloy, the lattice parameter of the newly developed alloy, and what could be the probability of it assuming a given range of lattice parameter. So this we are able to build based on the existing data set. So the foundation for all this is because we have an existing data set, and that data set is what has been represented in the form of the histogram, and from this histogram it is possible for us to estimate the probability of a newly developed alloy's lattice parameter and what could be its range. So probability of what could be the range of the newly developed alloy's lattice parameter. If it could be, what could be the probability of its lattice parameter lying in this range, what could be the probability of the lattice parameters lying in this range, and all this can be quantitatively described from this histogram representation. Now this histogram representation, again, it begins with creating specific bins and then populating, and then rather representing the population in each of these bins in a stacking up manner, or we have rather expressing or representing it in a vertical way. We have stacked up the population in such a way that the most populated bin is rather stands alone when compared to the rest. And again, the key aspect what histogram allows us to do is, without any association with any dependent variable, all that we have is just one independent variable. Just with one independent variable, the histogram representation enables us to calculate the probability of what could be the probability of the different ranges of the lattice parameter. So when I say that this range of lattice parameter has the highest probability, then what? The probability meaning the newly developed alloy can, or the probability of the lattice parameter of the newly developed alloy can fall into this, and this has the highest probability, so it can assume this range. So the probability of the lattice parameter of the newly developed alloy can assume the probability higher for it to assume this range here. The probability is rather completely lower to assume this range here. So the histogram helps us quantitatively state what is the range of lattice parameter. So what is the probability of the newly developed alloy assuming a specific lattice parameter, specific range of lattice parameter. Now, in addition to whether it is possible for us to rather make the histogram representation even more efficient by superimposing a distribution curve onto it. So what essentially we have done is, in this case, based on the histogram representation, what essentially it has been done is a curve is fitted onto the histogram representation. So the histogram representation, it helps us quantify the probability of the newly developed lattice parameter, newly developed Alois lattice parameter to one of the specific bins. And onto this particular histogram representation, we have fitted a curve over it. And this curve is what we refer to as the distribution curve. So essentially, the curve is rather an enhancement that we make to the histogram representation. And what essentially this curve does is, this curve is arrived by fitting the different distribution that we have arrived. So we have arrived at different distribution for different bins by stacking the population of the lattice parameter, and on to this distribution we have fitted a curve, and this is what we refer to as the distribution curve. So similar to that of the histogram, it is also possible for us to estimate the probability of the lattice parameter that a newly developed alloy can assume. So similar to the histogram, it is possible for us to quantitatively derive or quantitatively arrive at a probability that the lattice parameter of the newly developed alloy can assume. So in this case, what we essentially did was we measured, or we counted, or we considered the population of, when we want to know the probability of the lattice parameter falling into a given bin, we considered the population of that bin and took its ratio with respect to the overall population. And that is how we were able to estimate the probability in case of the histogram representation. We considered one bin, population of the one bin, we considered it in order to know the probability of this newly developed lattice parameter to fall into that bin. We considered the population in that specific bin and took the ratio of that population to the overall population. So that is how we were able to calculate the probability for the histogram estimation. However, in this case, the way we estimate the probability of the newly developed Alois lattice parameter falling into a given range by considering the area under the curve. Now supposing my interest is, I want to know what is the probability of my newly developed alloy falling in this range here, into this range here. So I want to know what would be the probability of the lattice parameter of my newly developed alloy falling into this range here. What essentially then I have to do is, I have to consider the area under the curve. So if I am able to measure the area under the curve, then I would be able to state that this would be the probability of the lattice parameter of the newly developed alloy to assume a range that is indicated by this red area. So if there is a specific probability of the lattice parameter to assume this range that is indicated in red, and this range can be expressed, or this range, this probability of the lattice parameter assuming this range can be estimated by considering the area under the curve. Here it was the ratio of the population in that bin with respect to the overall population. Here it is the area under the curve. Now considering this, considering the role of the histogram and the distribution curve, considering that one of the critical outcome of the histogram representation and also the distribution curve is understanding or quantifying the probability of what could be the lattice parameter of the newly developed alloy. So in this case we are focusing on the lattice parameter. It could be any conditions, any similar conditions, but one of the critical outcome that we get from the histogram and this and the corresponding distribution curve is that what could be the probability of, in this case, is the newly developed lattice parameter assuming a specific value. Since one of the critical outcome of it is the probability, we often refer to this as the probability distribution curve, and based on whatever the curve that it indicates is nothing but the probability here. So probability of our lattice parameter assuming a specific value. So it is possible for us to assume the y-axis to be the probability. It is possible for us, at least it is reasonable, quite reasonable for us to assume the y-axis of this curve to represent the probability. So we will get into the specific of it. We will introduce the y-axis and we will see what meaningful parameters can be attributed to this y-axis. But as of now, since this curve indicates rather what could be, or using this curve we are able to predict what could be the probability of the new lattice parameter falling to a specific range of existing lattice parameter. It can be assumed that this curve, it indicates the magnitude of the probability along the different lattice parameters. Now when you compare because both histogram gives us, or histogram helps us quantify the probability of a given range of lattice parameter, the same is rather done by the distribution curve as well. So you have a newly developed alloy, and you want to know what would be the probability of this lattice parameters of this newly developed alloy to fall into a specific range. For that you can use both histogram and also distribution curve. So if we are able to gain a certain degree of understanding from the histogram itself, so what is the need for the distribution curve? So we can see that is there any other advantage of to the distribution curve when compared to the histogram. So that is something that we have to look into, because we said that we are enhancing the histogram by introducing this distribution curve. So let us see what enhancement is being achieved when we introduce this distribution curve. So essentially distribution curve is based on the histogram that we already have, and when we introduce this histogram we claimed that this brings an enhancement to it. So let's see what enhancement has been brought to it. Now what essentially we can do is, supposing a particular set of data is missing while you are developing an histogram. So supposing you are building up an histogram and this set of data is missing. So based on the data you collected, because you have been considering a set of alloys and you have been measuring the lattice parameter of the set of alloys that you have previously developed and placing it in the different bins, and when you consider these different bins, the population of these different bins, all these remain intact whereas these data sets are missing. Now in that case, what be possible is, so in that case if I want to measure the probability of the lattice parameters lying between 0.45 or 0.4 to 0.45, then it would not be possible for us to estimate it because this particular data set is missing. Imagine a situation wherein we have similar distribution of the histogram, but one particular bin is totally missing, a data set pertaining to a particular bin is missing. Now in that case what we would end up having is, we would end up stating that the probability of the new lattice parameter falling into that particular bin's range is rather 0. So that would be our claim. But unfortunately, had we been looking into a large data set, we would have been able to include certain population or attribute certain population to this bin as well. So because our data set was rather limited, there were missing data on the existing bins. However, when we superimpose a distribution from the existing data set itself, and considering that this particular data set is missing, and including that or conceding that this particular population is missing, and just by considering or just using the existing data set, if we superimpose a function onto it, then this function, using this function, we will be able to estimate what would be the probability of the new lattice parameter assuming the range of the missing data set by considering the corresponding area under the curve. So this area under the curve would be something like this, and using the corresponding area under the curve, we would be able to rather give a quantitative approximate of a quantitative probability of what could be the range or the probability of the newly developed lattice parameter falling into the data set or the bin of the missing data set. So this missing data set is, even though primarily due to the limitation, since we don't have sufficient data set to populate this particular bin, it does not lead us to a trivial probability. So even though this missing data stems from the lack of our collection, the data acquisition, so because of the data set available to us is rather limited, and for that reason this particular bin is rather less populated, or it totally is not at all populated, it doesn't mean that the probability of the lattice parameter assuming this particular range is 0, because again it stems from our limitation it stems from this type of or completely or these populated or this type of missing data, it stems from our limited data set. So when we want to compensate for the limitation associated with the data set, then the distribution curve helps us. So what essentially distribution curve helps us is, it helps us estimate rather the probability associated with the missing data set. And again, this is primarily due to because we already have a distribution curve and we are finding the area under the curve. So all that you need to consider is, you need to consider the range that we are interested in, the range of the bin wherein the data set is missing. And when we are able to do that, we will be able to efficiently estimate the probability of the newly developed lattice parameter, assuming the range of the bin that is corresponding to the missing data set. Now, one other advantage of the distribution curve over the histogram is that whenever we are talking about the probability exclusively based on the histogram, we are rather talking about the probability in terms of the range of probability in terms of the range that is associated, that is completely coupled with the bin. So we cannot speak about rather say for instance, whenever we say that the probability of the newly developed Alois lattice parameter lying between 0.05 or 0.1 to 0.15 is the sum of the population of this particular bin to the overall population. So that is what we can rather present when we are focusing exclusively on the histogram. So what we have is the probability, the way we present the probability is rather restricted by the size of the bin. We cannot say what would be the probability of the lattice parameter assuming a value between 0.1 to 0.1 or 0.1 to 0.125 angstrom. We cannot predict a probability for such a range. We can only predict the probability of the range that has already been established by the bins when we are focusing exclusively on the histogram. We can say what could be the probability of the new lattice parameter assuming the range of 0.1 to 0.15, 0.15 to 2. We cannot say what would be the probability of the lattice parameter assuming the range of 0.125 to 0.175 because this is rather in between the bins. This range here, it disrupts the range that is established by the bins. So therefore, whatever probability discussion that we are making, whatever probability predictions that we are making, these are rather associated with. So these are rather confined to the ranges that are associated with the bins. Such restriction is not imposed by the distribution curve. So we can consider any such range, for instance 0.125 to 0.175, we can consider any such range, and by measuring the area under the curve through appropriate techniques, we will be able to rather quantitatively state the probability of any range. The range that describes the newly developed lattice parameter, it is not restricted to the range that is associated with the bins. So in case of the developing or in case of predicting the probability using the histogram alone, the range is rather restricted by the size of the bins. We cannot move away from the range that is established by the size of the bins. We cannot consider a section of this range or an expansion of this range. So we can only state that the probability of this range for the newly developed lattice parameter to assume is this much. So we can just focus about this range, and so on and so forth. So we can talk only in terms of the range that is associated, that is locked with or coupled with the bins. We cannot talk in terms of any other ranges. However, whenever we consider the distribution curve that is a product of the histogram, we can consider any range, and it gives us the quantitatively the probability of the lattice parameter assuming that range. And this is either not restricted by the range of the bins, because here we have a continuous representation, here we have a discrete representation, here we have a continuous representation. So histogram is rather a discrete, or it can be considered as a discrete representation, and what we have is a continuous representation here of the distribution. So therefore, whatever probability that we are talking about is locked with the bin range, whereas the continuous, it has no such restriction. And finally, it is possible for us, supposing the final advantage of the distribution curve is also linked with the missing data. That is, even if our population that we are considering, the data set that we are considering, even if it is not as extensive as this, even it is rather as only an half of this, even then, so even when you don't have these data points here, it is restricted. So all these data points we don't have, even then it is possible for us to arrive at such a distribution similar to this. The nature of this distribution can be arrived at. Similar distribution or curve can also be arrived at when we don't have such an extensive data set. So even with the limited data set, it will be possible for us to arrive at such a distribution curve. Unlike the histogram, the distribution curve, it is not significantly affected by the number of data sets that is available to us. Of course, it is influenced by it, but not as significant as the discrete representation of the histogram. So histogram, it is completely interlocked with, or it is completely dependent on the number of data sets we have, the number of data points we have, the number of lattice parameters measurements we have, not so much the continuous representation of it or the distribution curve. So when we say that we have enhanced the histogram representation and we have arrived at the distribution curve, what essentially we have enhanced, the way we have enhanced is, the one critical enhancement is it is possible for us to measure the probability of the data sets in a given bin that are missing, because we are considering the area of that or within that range, and this range is no longer restricted to the range of the bins. So we can consider any range, we can consider the ranges that lie in between these bins, and you will be able to estimate the probability for that ranges as well. And finally, even when we don't have expansive data sets, it is possible for us to arrive at a similar distribution curve. So the key takeaway points here is, when we have an existing way of understanding a given data set, we need to rather, the enhancement to that way of understanding would help us with the restrictions that are usually associated with the data set itself. So for instance, if we have two ways of handling data set, and one way is, or rather one approach is rather less significantly affected by the number of data points that are available to us, then we have to consider or prefer that approach over the existing one. We have two approaches here of understanding the probability or describing the probability. One is histogram and the one is the distribution curve. And now when you consider the influence or the effect of the size of data set in both of these representations, the effect of the size of data set is rather limited in the distribution curve when compared to that of the histogram. So therefore, this distribution curve is rather an enhancement of the existing approach, and therefore we often prefer estimating the probability using the distribution curve from that of the histogram. So essentially, we will wind this lecture up here, and we will consider the different forms of distribution in the subsequent lectures, and we will try to rather introduce some some mathematics into it, and we will try to introduce, like we discussed in the previous slide, what could be the possible y-axis onto this representation. So far we have been just considering just a one variable, and we have been talking in terms of the probabilities. We will try to rather build on this understanding in the subsequent lectures. I don't know, for some of you it could be rather a revisiting of the existing or something that you have already known about, but for some of you it might be new. So since the role played by these concepts in the data analysis are quite vital, so therefore we are trying to brush up our understanding of these different curves and of these histograms. So we will see ourselves in the next lecture. Goodbye.